So in your groups, I'm going to have you start with an activity rather than finishing with an activity today. So we have female bees develop from fertilized larvae, while male bees develop from unfertilized larvae. So that means that a female bee has two parents. It takes a male and a female to make a female bee. But a male bee only has one parent, the female. Okay. So a male bee has one parent, and we can make a diagram that traces the family tree of a male bee back 3 generations. So in a minute, I'll have you copy this down. So we have a single male bee, right, in the current generation. He came from a single female bee, right? It just takes one female bee to make a male. So this male's parent was just a female. Okay? But a female is made from a male and a female. Okay, so this female had two parents, a male and a female. Males have just a mom, females have a mom and a dad. Now, I'm going to trace back one more generation. This male has a single parent, a female bee, and this female has two parents, a male and a female. So I want you to go back 7 generations. Okay, so the next one, right, this female would have two parents, a male and a female. Females have two parents. This male has one parent, just a female. And this female has two parents, a male and a female. Okay. And we can count the number of bees in each generation. So in this first current generation, we're looking at a single male bee, one bee. Okay. And when we go back a generation, it had a female parent, still just one bee in that generation. When we go back another generation, because this female had a male and a female parent, there were 2 bees in that generation. And then 3 generations back, we had 1, 2, 3 bees. And when we go 4 generations back, we've got 1, 2, 3, 4, 5 bees. So keep working your way back. Go back 7 generations. Write out the parentage and count how many bees there are. Any number is the sum of the 2 numbers right before it. So what number would come next in the list? 34. 13 plus 21 would be 34. And then the next number in the list would have to be 55. Good. Okay, so we already did this. 34, 55, and the next number on the list would be 89. Yeah. So that's the number of bees that we would predict would be 8, 9, and 10 generations back. So let's say you're a beekeeper. This would be practical, right? It's not that funny. So this pattern, so we've discovered a pattern in the reproductive habits of bees. Okay, so in and of itself, that's interesting. Like, that's a weird pattern to find that bees are doing, right? What we're going to discover in this chapter is that we see this pattern over and over and over again in nature, in art, in architecture. You're going to see it everywhere, and you're going to be blown away, I promise. It has so many applications. You're going to say, stop showing me applications of those numbers. Okay, so let's just count the male bees. So I just wrote out the populations again. You have them written in your notes. If you just count the number of male bees in each generation, we've got 1, 0, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, 8. What do you notice about these numbers? Same pattern. Every number in the list is the sum of the previous two. The first two numbers are different, 1 and 0, instead of 1 and 1, but then the pattern picks right back up. Right, what if I count female bees in each generation? I've got 0, 1, 1, 2, 3, 5, 8, 13. Same pattern if you count just female bees. Again, the first two numbers are different. So here it was 1, 0. Here it's 0, 1. So the first two numbers are different, but the pattern is the same, where every number is the sum of the previous two. So remember, a sequence is just an ordered list of numbers, just a list of numbers. In the B problem, this is our list, 1, 1, 2, 3, 5, 8, 13. Okay. We use our shorthand notation that we developed last class to talk about any number in the list. So we're going to denote this sequence as F sub n. F because these are known as the Fibonacci numbers. So F sub 1 would be 1, the first number in the list. F sub 2 is also 1, the second number in the list. F sub 3 means the third number in the list, so that would be a 2, right? Third number in the list is 2. The fourth number in the list is 3, and the fifth number in the list is 5. F6 is 8, F7 is 13. So this is just the notation we learned last class. So according to my answers from the B activity, F8, right, would be 21. No, because when we wrote down, this was generation 0 when we were writing down the B's, but it's F1, it's the first number in the list, so they're all off by 1. Okay. So F8 is 21, F9, 34, F10, 55. Right, so my list is just 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So F8 is just the 8th number in the list. You just go 1, 2, 3, 4, 5, 6, 7, 8, 21. F9 is 34, F10 is 55. All right, so we want to write down a rule, formula for finding the Fibonacci numbers. We're going to write down a recursive formula. Okay. So we talked about recursive versus explicit formulas last class. So, and it helped to always write down the rule in English first, and then we can kind of translate it. So we've already done that. We said any number in the list is the sum of the previous two numbers. So now we can translate this to the symbolic notation that we learned last class. How could we represent any number in the list? Anyone remember how we do that? N would be the nth place, yeah. It's the nth place, so we'll have F sub n. Okay. Because we denote the numbers in the list by F with a subscript, right? Subscript is the n. The subscripts are the n's. Okay. So we can talk about any number in the list. Like I can say F17. That represents the 17th number in the list, right? So if I want to find any given number in the list, I would say call it f sub n. Okay. It is, that's an equal sign. F sub n is, any number in the list is, the sum of the previous two numbers. The word sum means add, right? So I'm going to add the two numbers that come before f sub n. Well, what number comes right before f sub n? F sub n minus 1. And what number comes before that? Fn minus 2. So there's my rule. This is my recursive rule for the Fibonacci numbers. This says that the nth Fibonacci number, which is just a generic number in the list, is equal to the n minus first Fibonacci number, which is the number right before the nth. So for example, this says that f sub 14, right? If I make n 14, it says that that should be equal to f sub 13, right? Because n minus 1 is 13. 14 minus 1 is 13. Plus f sub what? Yeah, because 14 minus 2 is 12. So this is called a recursive rule. And in order to use a recursive rule, you need to have something to start with, right? If I want to calculate, say, f sub 3, I need f sub 2 and f sub 1. And if there's no f sub 0, right, f sub 1 is the first number in the list, I have nothing to build it from. So I need two foundations or seeds, right? So I have to give you the first two numbers in order to use this rule. So they're called the seeds, and they are 1 and 1. Okay, so if we know, I'm just going to tell you, the 39th Fibonacci number is 63,245,986. And the 40th Fibonacci number is 102,334,155. How could you figure out what f sub 41 is, the 41st Fibonacci number? Add the 39th and the 40th. Any Fibonacci number is the sum of the two Fibonacci numbers right before it. That's what the formula we wrote down a minute ago said. In fact, let's write it down really explicitly in detail. So f sub n is f sub n minus 1 plus f sub n minus 2. So if I'm looking for f sub 40, that should be the sum of f sub n minus 1 would be 40 minus 1, and n minus 2 would be 40 minus 2. N in this case is 40. So this is f sub 40 equals f 39 plus f 38. Oops, sorry, I'm looking for 41. F41, 41 minus 1, and 41 minus 2. So F41 is F40 plus F39, which I happen to know. I was given those two numbers. So I add them up. Use a calculator. I get 165,580,000. 141. To use a recursive formula, so a recursive formula calculates the value of a number in the list using previous numbers in the list, right? But you can only go back so far, right? Once you get to the first number, there is no number before that, right? So there's no way to calculate it using the recursive rule. So I have to tell you what the first number in the list is, and that's called the seed. So you plant the seed, and then you use the rule to grow the list. All right, so f sub 41 is the sum of 39 and 40. How could I get f sub 38, the number before the 39th?
Wait, you still need the one number before it, though, right? No, not a seed.
Not a seed. The seeds are 1 and 1, the first two numbers in the list. Yeah, you would. So let's explain why that is. So f sub 38 plus f sub 39 will give me what? F sub 40. Any two numbers in the list, you add them together, you get the next number in the list, right? So we're going to do a little teeny bit of algebra here, right? Subtract f39 from both sides. So we get f38, because these cancel, is equal to f sub 40 minus f sub 39. So I happen to know what these two numbers are, 40 and 39. So I can just subtract them. So I have 102, 334, 155 minus and I get 39,088,169. I already forgot it. 39. So we can use this rule. Each number in the list is the sum of the previous two to go forwards in the list or backwards in the list, right? If you know two consecutive numbers, you can find the next one or the previous one. Okay. So Fibonacci is credited with the invention or the discovery of this list of numbers. His real name was Leonardo of Pisa, but Fibonacci means son of Bonacci. His father directed a trading post in Africa. He was an Italian, and his father directed a trading post in Africa, and Leonardo traveled there, and that's where he learned about Arabic numerals. Okay? Arabic numerals are the numerals we use today, the exact numbers, and he introduced them to Europe. And before the Arabic numerals were introduced to Europe, we used Roman numerals. Europeans used Roman numerals, and they were a nightmare. Roman numerals were awful, and Fibonacci introduced the Arabic numerals. So, yay, he's a hero. To Europe, yes. These are called Arabic numerals. Yeah, yeah. Yep, the numbers we currently use are Arabic. Mm-hmm. So even simple computations were really difficult with Roman numerals. And being a merchant, right, using Arabic numerals was really great, being able to keep track of, you know, his stuff and money and things like that. So the work that he's most known for, even though his biggest contribution was the Arabic numerals, the work he's most known for, and the one that contains the B problem that we just talked about, is called Liber Abaci, a book that he wrote, written in 1202. So the original phrasing of the problem was in terms of rabbits, not bees. This is the problem that he wrote in his book. He said, a certain man put a pair of rabbits in a place surrounded on all sides by a wall. So you've got 2 rabbits in an enclosed space. And it says how many pairs of rabbits can be produced from that pair in 1 year if it's assumed that every month each pair makes a new pair, which from the 2nd month on becomes productive. So to translate, okay, we're assuming that any pair of rabbits can procreate. So this is not necessarily a true assumption, but we're assuming it. Any pair of rabbits can reproduce, and that it takes them a month to reach reproductive age, right? So for a month, they're babies, and then they can reproduce. All right, so let's see what happens. We start with a pair of rabbits. So we'll use big R to represent adult rabbit. And we know that those can reproduce, and little r will be a baby rabbit. And those can't reproduce. So if we start with a pair of rabbits, so we've got R and R, and we'll call this month 0, right? Time 0, we'll put 2 rabbits in there. 1 month later, those original 2 rabbits still live in there. They're still there. Another assumption we're making is that none of the rabbits are going to die over the course of this year. And these 2 rabbits were adults, which means that they produced a new pair of rabbits that are babies. Okay, so now, after 1 month, we have 4 rabbits in there. 2 adults, 2 babies. The next month, these 2 rabbits are still there. The 2 baby rabbits are now adults. And during this month, when there were 2 adults and 2 babies, the 2 adults produce another pair of babies. They reproduce every month. So these 2 capital R's in month 1 produce another set of babies in month 2. So these are the same guys. These are the same guys. And then these 2 capital R's produce the baby R's. And then in month 3, everybody's still alive, right? Everybody's still there. The 2 sets of adults are still there. This set of babies grew up. And in month 2, there were 2 sets of adult rabbits. They each produce a pair of babies that are born in the next month. So I have R, 2 pairs of babies. Let's do 1 more month, just see what happens here. Month 4, everybody's still there. 3 sets of adults remain adults. My 2 sets of babies become adults. And I had 3 sets of adults in the previous month, each of which is going to produce a pair of babies. Is it exponential or is it Fibonacci? So if we count the number of pairs in each month, we've got 1, 2, 3, 5, 8. How many do you think will be in month 5? 13. Yep. This is the Fibonacci numbers. Yep. So we also see the Fibonacci numbers in rabbit, the rabbit reproductive patterns. We're counting pairs of rabbits, whether they're adults or babies. So interesting. We see the same set of numbers pop up in a seemingly totally different place. So this is where the numbers got their name. Fibonacci published this problem in a book, and noted this interesting pattern of numbers. He said, oh, look at these numbers that show up. Each one is the sum of the previous two. Okay. So some claim that the Fibonacci numbers occur in nature. Some are dubious of this claim. We will see lots of examples of places where we see it. But before we do that, we're going to study some ratios of Fibonacci numbers. So I want you, each of you, to calculate the 1st through the 20th Fibonacci numbers. Just make a list of F1 through F20. And then we're going to fill in ratios of Fibonacci numbers. Okay, so on the left, so you're going to make 2 columns. On the left, just fill in the Fibonacci numbers. You want to go up to F20. So make a list of 20 Fibonacci numbers on the left, and then I'll explain the ratios once everybody has those down. Okay, so we want to have 20 Fibonacci numbers. So I'm going to write them vertically. 1, 1, 2, 3. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe I'll just do 10 in a column. Okay. Well, maybe, but it shouldn't. All right, so then the rest of my Fibonacci numbers, my next 10 are going to be 89, 144, 233, 377. Yeah. And that's it? What? 85, 84? Okay. Okay. So now what I want you to do is look at each pair of numbers. Okay? So and take the ratio of the two. So I'm going to look at the 1 and the 1, right? So this is going to be 1 over 1, which is 1. And then I'm going to look at the 1 and the 2. Put the bigger one over the smaller one. So I'm going to have 2 over 1, which is 2. And then look at the next pair, the 2 and the 3. I'm going to take the ratio of the bigger over the smaller, 3 over 2, which is 1.5. Move down a set. Look at the 3 and the 5. 5 over 3 is 1.333, repeating. And then look at the 5 and the 8, right? 8 over 5 is 1.6. I want you to go through and do these ratios, calculate these ratios for every pair. Okay, just go through your whole list. And I want you to keep 5 decimal places. Okay, so if you take the ratio, put it in your calculator, if it has a lot of decimals, write down 5 of them. It's a little bit tedious. At first, they seem to be, pretty different. They start coming out pretty different. And then we start settling in at 1.6 something, right? And then as we continue taking ratios, they all start coming out to be 1.61803 after a certain amount of time. 1.61803. So let's test if that pattern holds way out in the list of Fibonacci numbers. So here's the 39th and 40th. I gave you those earlier in class. If I take the ratio of the 40th over the 39th, right, the bigger over the smaller, let's see what we get. So my bigger one is F40, 102, 334, 155, divided by 632, 45986. My ratio is 1.61803. And here's the 49th and 50th Fibonacci numbers. If I take the ratio of those two, see if I get the same number. 125,862, 69025 divided by 77787, 42049, 1.61803. So the further out you go in the list of Fibonacci numbers, we keep getting this same result. After 5 decimal places, it starts to change a little bit. But the further out in the list you go, like once we're out 50 places, they start to agree to 6 decimal places. Right? Once you go out to 100 places, 100 numbers in the Fibonacci list, the numbers will start to agree to like 6 or 7 decimal places. So it seems like they're converging on a specific number. That number is called the golden ratio. Okay. It's called a ratio because we're taking ratios of Fibonacci numbers. And it pops up often enough that it has a special name, the Greek letter phi. Okay. So just like pi is important enough that we have a symbol for it, phi is important enough that we have a symbol for it. Yep, it's like a circle with a vertical line through it. Phi. And we know it's about 1.61803, but then the rest of the decimals we're not quite sure of because they keep changing as we go further out in the list of Fibonacci numbers. It's spelled P-H-I. It's a Greek letter, yeah. But it's pronounced phi like F-E-E. Some people pronounce it phi. Just varies. I don't know which one is actually correct. Okay, so in mathematical notation, this is not, you don't have to remember this. It's just fancy. We're taking ratios of Fibonacci numbers, right? The bigger one over the one, any Fibonacci number divided by the one before it. And as we let n get really big, right, we take n going really big, really far out in the list, this ratio approaches the number phi. Okay. So another way to write this is we could say as n approaches infinity, as n gets really big, the ratio of two Fibonacci numbers, any Fibonacci number over the number before it in the list, approaches phi. This is kind of a nicer notation, I think. And phi is approximately 1.61803. So this number originated in a context completely different from the rabbits. Okay? Even though it's intrinsically related to the Fibonacci numbers, that is not where we first discovered this number. This number first came up when people were deciding, there was discussion, saying, what's the prettiest way to divide a line segment into 2 pieces? Okay, so I've got a line segment, or a piece of string. I'm going to cut it so it makes 2 pieces. Where should I make the cut so that it looks as pretty as possible? Yep. Why is it that number? That seems kind of a random number to decide if we were just having this conversation, right? Because it's feet, right? So the answer is, we decided, somebody decided, the ancient Greeks actually decided, that we should make this cut in such a way that Draw it again. I'm going to make the cut, say, right here. And let's just pretend that this thing has length 1 unit. Okay. So if this whole thing is length 1, then I'm going to have this piece be x, and this piece would be 1 minus x. So the prettiest way to make this cut is to say, well, the ratio of the short piece to the longer piece should be the same. Okay, so if I take the ratio of the shorter piece to the longer piece, it should be the same as the ratio of the longer piece to the whole. The ancient Greeks were sort of obsessed with ratios. They were trying to always set ratios equal to each other, and it was almost like religious how much they believed in rational numbers and how much they loved them. So they were always taking the ratio of one thing to another and saying, does it equal the ratio of this thing to this thing? And they were always comparing ratios. And they said, you know what would be nice is if I cut this so that the long piece divided by the short piece, or vice versa, the short piece divided by the long piece, should be the same as if I do the long piece divided by the whole line. And if I put in my variables the way I set this up, this is going to say x to 1 minus x, short piece to the long piece, should equal the long piece, which is 1 minus x, to the whole line, which is what is the length of the whole line? 1. So now I have a proportion to solve. And once I solve it, I'll get a value for x, which will tell me exactly where to place this cut. He was just jumping to conclusions. He knew that we were talking about phi, so he guessed, because phi is 1.618, and he took that 0.618 and said 61.8%. Right? He was jumping to conclusions. Don't worry about it. I have this proportion to solve. Once I solve it, I will know where to make the cut in the prettiest place possible. So how do you solve a proportion? I got to find the value of x. That's my goal. How do I do it? What does that mean?
Well, if you're assuming it's 1 unit, you just subtract what you know that percentage is going to be from.
No. You can't assume you know the answer while you're trying to find the answer. Yeah, we got to solve for it. How? We're going to use a little algebra. You guys remember how to do it? Cross multiply. Yes. Cross multiply. Right. So I get 1 minus x times 1 minus x equals x times 1. Multiply the upper right, lower left, and upper left, lower right. Set them equal. Anybody this looking familiar?
It looks familiar, but I can't. It's the 1 minus x and 1 minus x.
So what I did is I didn't actually multiply them together yet. I just wrote 1 minus x times 1 minus x. I didn't do the multiplication yet. When I multiply them, how do you multiply two binomials like that? FOIL, yes. We remember a little bit of algebra. So we have 1 minus 2x plus x squared, right? First, outer, inner, last. Okay? And that should equal x. So I have an equation with x squared. Who knows how to solve a quadratic equation? You factor it if you can. What if you can't?
You make those 2 brackets, and I'm doing it right here.
Yeah, so I'm going to subtract x from both sides to make one side 0. So I have x squared minus 3x plus 1 equals 0. Factoring. Yep. Right, yeah. Yeah, if that was a 5 and a 2, you would go, oh, multiply them together and you get 10. Yeah. So we're just generalizing. You still just multiply them together. I might have messed something up. Short to long equals long to whole. No, that's right. So this is a quadratic equation. The prerequisite for this class is Math 105, which is the basic intro algebra course, which does not get to learn how to solve this equation. Yeah. So this equation, you may or may not know how to solve. So I'm just going to tell you what the answer is. We're not going to go through the process of solving it. Is that okay? Okay. So exactly. So the techniques that you've learned so far in this class, in your algebra class, was combine like terms, get all the x's on one side, the numbers on the other, right? Does that sound familiar? But you're right, there are no like terms. There's nothing else to combine, and this doesn't look like something I know how to solve. So this has a technique that you have not yet learned in order to solve it. So I'm just going to tell you what the answer is. I'm not going to show you the technique. No, because it's not important. Okay, so let's see. This is the solution. 1 plus the square root of 5 divided by 2. Let's type it into the calculator. So I'm going to do the square root of 5, add 1 to it, and divide by 2. And what do I get? 1.61803. I get phi. Yep, x equals phi. That's the answer. Crazy, right? So the Fibonacci numbers that we first discovered by looking at the reproductive habits of bees, right, led us to the golden ratio by looking at ratios of the Fibonacci numbers, which is related to something that we find aesthetically pleasing in art, how to cut a line in 2 segments that is pretty. Yep, right, but we were doing it. Yeah. Yep. People were doing it, I should say. We're using that ratio without knowing what it was or where it came from. So this number is called the golden ratio, the golden mean, the golden section, the divine proportion, about a billion other names. And like I said, it started being studied by the Pythagoreans, some of the ancient Greeks. And the way they studied numbers and ratios of numbers was religious. They studied it with like a religious intensity. And that is how they explained the world. Like instead of, using a religion and gods, they explained the world with numbers and ratios of numbers. And that's why this is sometimes called the divine proportion, right? Because it had a lot of meaning in how it explained the world.
Does that have to do with the sun thing?
Don't know. A sundial? I don't know. So we have this cool property of phi that we know phi squared. We were trying to solve the equation x squared equals x plus 1. No, hold on, I messed up my equation somewhere.